Okay, limiting sums of geometric series. Now the thing about limiting sums of geometric series is that they exist where the absolute value of r is less than 1. Another way of saying that is that r, the common ratio, must be between -1 and 1. Of course, if the common ratio is 1, well, you don't have a geometric series going at all, do you? So it must be between -1 and 1 exclusive. Alright, so this one you might want to press pause and read the question, and I'll start work on it very soon. So what's the limiting sum of the series 81 plus 27 plus 9 plus, and it goes on forever and ever. So when we find the limiting sum of the series, we're finding what the series sum is tending to without actually ever reaching. So there's a very simple formula in the case of limiting sums, and it goes like this. The limiting sum, that's the infinity sign, or it's supposed to look like that. So the really a way of saying it is the sum of an infinite number of terms is simply the first term divided by 1 minus the common ratio. Now here we know that a is equal to the first term, so it's 81. The common ratio is found by dividing a term by its previous term, so we can go 9 divided by 27, which equals 1/3. Okay, and now what we do is we simply substitute our values for a and r. Oh, I didn't say that equals r, did I? Anyway, r into our formula. So we're going to get rid of this a bit and say that the limiting sum is equal to a was 81 divided by 1 minus 1/3. And that equals 81 divided by 2/3, doesn't it? Okay, so that's equal to 81 times 3 divided by 2. And 81 times 3 is 243 divided by 2. And that's a reasonably satisfactory answer, but if you want to present it as a mixed number, it would be 1, 2, 1.5. And that's our first example. Our second problem, so press pause while you read the question. Now here we can think of our fraction, as our recurring decimal, as equal to 4/10 plus 3/100 plus 3/1000, etc., etc. Can't we? Just making use of the place values of our digits here. Okay, so once we think about it that way, we can say that our limiting sum is equal to 4/10 plus those 3's, like so. And that means really that what we're going to do is we're going to bracket this 4/10 off and treat the the 3 digits as a geometric series in their own right. Okay, so let's have a think about that. Well, what we can do is write our limiting sum series in the following way. We can say that S infinity is equal to 4/10 plus. Now looking at back up here, a is equal to 3/100, and we're going to go 1 divided by the common ratio. Now hopefully you can see that the common ratio is 1/10, because you're multiplying that by 1/10 to get to there, and you'll multiply that by 1/10 to get to the next term, etc., etc. So the common ratio is 1/10. And let's just tidy that up a bit. It's going to equal 4/10 plus 3/100 over 9/10, and that equals 4/10 plus, invert the bottom fraction, invert that one and change it to a times. We are going to get 30 over 900. Okay, So that's pretty good. Now what we need to do now is just tidy up that last line. Let's put that up there. And what are we going to say about this? Okay, so looking at the 4/10, what I'd like to do is express that 4/10 in terms of 900, so I've got a common denominator. So I can get from 10 to 900 by multiplying by 90. So what I do is I multiply the 4 by 90 and write my common denominator as 900, and 4 times 90 is 360 plus 30 over 900, and that equals 390 over 900. Certainly that can be simplified, which was what the question was asking us to do. So just from my calculator, I am seeing that what I've got is 13 over 30. Okay, so that's what we're saying there, is that 0.43 reoccurring is equal to 13 over 30. And that's the end of that example. Third example, we can use sigma notation to express a limiting sum type problem, and there's no great mysteries to it. This really is in the format such that you can say that the 2 there is equal to A, and your common ratio is sitting there in brackets. Okay, so that, remember a geometric series is normally takes this form. So that's where I'm getting the A and the R from. Okay, and once you realise that, it becomes very simple. So we can say that the limiting sum of this particular series is equal to, now A is 2, 1 minus R, which is a third, so that equals 2 divided by 2/3, and that will equal 3. Okay, nice and simple. Okay, fourth example. Now, this one's got a bit of a trick to it. The first thing to notice is that our series is not expressed in standard form. We'd expect to see an n minus 1 there, remember? And there's no A term, so you might be tempted to conclude that A is in fact equal to 1, but it's not. So let's solve this by thinking about, well, what is the first term and what's the second term? So to find the first term, you simply substitute n equals 1 into this expression here, and you'll find that it's, well, 7/8 to the power of 1 is 7/8, isn't it? Oops, 7/8. And the second term is going to be found by substituting n equals 2 into this expression. So 7 squared is equal to 49, oops, and 8 squared is equal to 64. Okay, so it turns out that A is equal to 7/8 and R is equal to 49 on 64 divided by 7/8. Oops, 7/8. Okay, and that's going to equal, in fact, 7/8. Now you could probably see that back up here anyway. To get from there to there, you're going to multiply by 7 over 8, aren't you? Okay, so let's get rid of that and solve this. Alright, so the sum of the infinite series is equal to A over 1 minus R, of course. Now in this case, A is equal to 7/8. 1 minus our common ratio is 7/8. So that equals 7/8 on 1/8. And that's equal to 56 on 8, remembering that if you divide anything by 1/8, it's the same as timesing by 8, so the 8's kind of cancel out there. And that's equal to, whoops, that's equal to 7. That's our final answer.